So, welcome everyone to today's webinar on high temperature heat flow meter measuring thermal conductivity of thermal barrier materials. This is a C-Therm partner webinar. We are joined today by Nikica Jurcevic from ZFW. He'll be doing, I'd say, most of the heavy lifting in today's content. I'll be passing it over to him shortly here after a brief introduction. So just want to kind of set the stage here, as we were going through the content of today's webinar, really looking different areas of application, like who is going to, let's say resonate with this. A few different things really came to mind. Material scientists, R&D engineers in the space of, insulations, thermal barrier material, would be certainly one that we'll be talking about quite a bit. Overall thermal management specialists, so whether you're dealing with the materials going into various systems, maybe like the, EV components, or if you're maybe looking at the overall battery safety and pack designs as well. Some of the content in today's presentation will be kind of, I'd say, targeted towards some of these areas. And of course, the purpose of today is really looking at high temperature applications. So, saw this stat from a few years back, but when we look at a lot of, whether it's electronics or just different, component systems, one of the major drivers for failure is temperature. Now, there are other aspects, of course, but when your material is essentially going into these environments, high temperature, extreme heat conditions, how are you able to prove its performance out? How are you able to design those systems to ensure they can accommodate some of these extreme conditions? So this is really, I'd say, some of the aspects that we'll be going into today throughout the session. So before I hand it over, I just want to give a quick introduction here from C-Therm side. So C-Therm, we're focused on thermal conductivity instrumentation, specifically in the transient class of measurement technique, working with researchers, manufacturers, and various professionals across a variety of different industries. All with the goal of really simplifying thermal conductivity testing for the materials of tomorrow. We've been fortunate enough to work with some really great organizations over the years. I wanted to share one testimonial here from folks that we worked with at NRC Canada. They made a comment on our system that overall found the C-Therm's Trident thermal conductivity measurement system to be reliable and user-friendly. The performance has been efficient in delivering accurate and consistent results. So definitely, if you're interested in kind of hearing some other stories about groups that we've had the fortune to be able to work with, definitely feel free to check out some of those on our website. So for today's agenda, as I said, I'll be kind of kicking us off with just a little bit of an introduction. Then I'll really be handing it over to Nikki to go over, introduce himself, ZFW, but go into some of the testing challenges in this application space. Really go over a lot of the instrument background and theory behind the high temperature heat flow meter systems that they have, and as well as sharing some application data. And then I'll be coming back on with him later on for the Q&A. So quick introduction here from my side, thermal barrier materials, high heat, and like really why these measurements matter. So as I kind of led into at the beginning, any industry that you're dealing with high temperatures, extreme temperature conditions, they ultimately revolve around the utilization of thermal barriers in some fashion. These can take on different forms, whether they are, aerogel components, sheets of materials, foams. These are here to act as barriers to negate that heat transfer in terms of protecting some of these systems. And when we're talking about heat transfer, of course, thermal conductivity plays a very significant role here. So again, whether you're dealing with more industrial applications, the EV side, aerospace and some of these hypersonic applications, these are certainly areas where this type of test is quite relevant. Did want to just make a quick note because oftentimes when we talk about, insulative applications, many groups are interested in thermal resistance or just actually, differentiating between what thermal resistance or R value is compared to thermal conductivity. But your R value is unlike conductivity, which is an intrinsic property, is dependent on the material thickness. So knowing that if you're talking in this space about conductivity versus R value, you have to take into consideration the thickness of the sample that you're dealing with. And this can have some, interesting implications because, if you were dealing with a system and you're trying to achieve a certain R value, well, one of the simple ways to increase your R value, taking the same material and just, let's say, doubling the thickness, that can have a role there. But many times, some of these systems you're confined on space or there are, tolerances that you have to be within. Well, if you're dealing with a specific thickness requirement, how do you increase R value if you can't increase thickness? Well, that's where, of course, the thermal conductivity comes in. So by decreasing your thermal conductivity, being more insulative, you'll get a higher R value at the same outputted thickness. So something that I see come up quite a bit there, and kind of some groups have questions about it. So just wanted to drop in that little tidbit there before going much further. Now, some of these aspects, will be discussed in Nikki's section here, but why high temperature is uniquely challenging? Well, you can imagine some of these materials are going to behave differently compared from, let's say, room temperature to high temperature. You can get expansion or physical changes within the material. How do you deal with that when it comes to, again, setting up the system for measurement? At higher temperature conditions, thermal radiation also starts to play a role. How does that impact the effective thermal conductivity measurement? These are some of the kind of aspects here that we'll be taking a look at, and really looking at again, the high temperature heat flow meter system in general. So before going any further here, wanted to do a quick poll with you folks. Fine, we've kind of introduced these recently, so we'll take maybe 20, 30 seconds. You should see this show up on screen there. If you wouldn't mind, folks, just kind of going through and kind of putting in your answers there, and we'll kind of take a look. So really, we're kind of seeing like what applications are you using high temperature thermal conductivity data for? What are those kind of areas? I'd be interested to see what folks are saying here. So we'll give this maybe another 10 or 15 seconds or so. Alrighty. So let's see here. End the poll. Share some results here. So all right, yeah. So it looks like, a little bit of a mix here. So we're seeing some, I'd say about 50% coming from the battery pack space, seeing some aerospace and defense, some industrial applications. Interesting. So yeah, no, thank you for sharing that. We try to kind of, getting the information from you guys firsthand really helps us kind of guide on how we do these types of webinars and the content in the future. So thank you very much for sharing, everyone. All right. So at this point, that kind of brings it to the end of that little bit of an intro. I'm going to hand it over to Nikki to take us through the bulk of today's content. So I'll stop sharing here and over to you.
Yes, thank you, Aria, for the introduction. Also a warm welcome from me. So I hope you should see my screen. Just
all good there.
Yes, just a little bit of difficulties here. One moment. So now, perfect. Okay. Yes, as Sarah mentioned, my name is Nikica Jurcevic, and I'm a thermal engineer at ZFW in Stuttgart, Germany here. ZFW stands for Zentrum for Wärmemanagement, which translates to Center for Thermal Management. We are a institute-like company, um, yeah, close to the cooperative state university here in Stuttgart. And we're about 15 peoples working all different kind of projects in the thermal management space. And yeah, I'm pleased to yeah, introduce you to our newest tester, the guarded heat flow meter tester. My goal is basically to show you yeah, like a little bit of a history how we reached the point today with the tester, the methodology, and yeah, the tester specifics, so to speak. So, um, as I mentioned, we are called the Center for Thermal Management, and for us, basically, this means cooling. So, cooling is usually high conductive materials. This is our field for 20 years, characterizing those kind of materials, consulting, building testing methods around high conductive materials. And about 5 or 6 years ago, we started to receive um, different inquiries, especially from German car companies, regarding the characterization of battery cell spacer materials. And battery cell spacer materials, they are basically used to prevent the thermal propagation of a battery pack. So basically, if one battery cell goes off, to delay or even prevent the thermal breakthrough to the other um, cells, to the neighboring cells. So they are basically put in between the cells. And the efficiency of these cells depends on various factors. This is the thermal conductivity of the material or the thermal resistance. Um, then you need to keep thermal mechanical effects you have to control them as well or understand them. So in this case, it's mostly the pressure. When one battery goes off, you will compress the pad and it might behave totally different than in the basically in the beginning of life effects. And the other one is the thermal stability. So how does the material behave under high temperature? And all this requires application focused testing, which we try to achieve with our method. Just here some challenges. You can see different kind of materials. So in the last 2 years, we did a lot of testing of different kind of materials. I would say we tested between 100 and 150 different kind of customer samples. And the challenge is basically that they, at this point, all behave very differently than to materials that we know in the high conductive world. So we have different kind of structures. We have aerogels, we have ceramic fiber materials, we have multi-layer composites with mica and polymers, and yes, and the thermal conductivity is very low. So we are in the range of 0.02, which is basically still air, up to maybe 0.15 or 0.15 to 0.2 watt per meter Kelvin at the elevated temperatures. The thickness range is usually from 2 to 5 millimeters, but it can go maybe also for different kind of applications up to 10 millimeters. And it having very low thermal conductivity, the thermal resistance is very high. So it needs special kind of methodology to test it. Also, the surface pressure is in the range of 0 to 4 megapascal, and the temperature at which we test is up to 850 Celsius. So I just wanted to introduce a quick slide about theory. I already realized you use K for thermal conductivity. Here in Germany, it's usually K, or more often it's the lambda value. So just to make sure that you understand what I'm talking about. So the thermal conductivity lambda is basically the ability of a material to conduct heat, and this is defined by a set temperature difference across the sample or the cube, and through a set length and across cross section and during a time, basically. And you can see here basically the formula how you can derive it. And the thermal resistivity is basically the inverse of the thermal conductivity. So it's the ability of material to prevent conduction of heat. The resistance itself is based on the thermal resistivity, but it's an absolute value, so it includes the thickness and also the area of the material. And then we like to use the term effective on all those mentioned values. Effective values are basically the properties of the bulk material included with external effects. Here's basically just a quick example to show if you have an ideal surface and you have a heat flow going through, then you have perfect heat flow lines, and that is the ideal world. In the real world, you have a rough surface, for instance, and you will not basically have an ideal heat flow in the material. And these added effects are basically called effective values. Okay, then let's get a little bit deeper in the materials. You see a cross section of this material, and we test with a very hot temperature on the hot side and a cold temperature, like in the range of room temperature, of on the bottom side of the material. And the unique thing about this material or this field is the big temperature gradient. So in uniform materials at low temperatures, you usually don't have that much of a temperature effect on the material, and the heat is basically transported to three different methods here. It's the conduction, which is a function of the temperature. It's the convection, which is also a function of the temperature, but this can change depending where you are in your cross section, in your Z axis here, because the convection might be different because you have different kind of gases through burning or whatever in the material. And then you have the big factor as the radiation. This is a function of the temperature to the power 4. So you will usually have a much higher thermal conductivity in the upper, close to the hot side, than in the lower areas. And this is basically shown here that you can have, depending on the sample, different kind of temperature profiles in the material itself. And that's why we say it's important to test these materials at the application close temperature gradient. So, and then we have added effects like the melting, degradation, evaporation, and so on. So the thermal conductivity is a function of the temperature, but also the temperature difference in the material. So when we started in this field, the customers which came to us and asked us for help in the testing field usually had a so-called hot-cold side test to compare the materials, which is basically a hot plate which is pressed on the sample. And what they do is they compare the cold side temperature on the cold plate and compare different kinds of materials. Now, this is a quick and easy and a good way to compare materials, but you can't really derive any data for, let's say, for simulation or for prediction or for data sheets, and that's why they came to us, especially for input for simulation. And we had established a hot wire method yeah, way before, which we in the beginning used for this kind of testing. So basically, the wire is put in between two samples and is you have a fixed measuring current going through, and then you can basically directly derive the thermal conductivity of the material. This is done in a furnace oven at elevated temperatures. But the point here is basically that you don't really have a temperature gradient in the material. And as I said in the years with literature studies, also with our customers, we came to the conclusion that we need a high temperature gradient to test it effectively. And that's basically how we then designed our tester method in the beginning. Okay, so there are different kind of standards which can be used in this area, but we had the idea to establish our standard of the high conductive world, the ESTM D5470, which is basically used for thermal interface materials, so very good conductive solutions. But this is a field which we have, yeah, quite a bit of experience in about 15 years, and we wanted to make it work for testing this kind of low conductive materials. So the method itself is also called a steady state cylinder method. Basically, you have a upper meter bar and a lower meter bar. So you have a hot side on the top and a cold side on the bottom. You have a heat flow going through the sample. And now you can derive basically with the formula for the thermal conductivity the properties of the materials itself. And you are using the temperature gradient in your known meter bars to determine the heat flow, which you need to calculate those values. So here you can see the temperature over the position, and then you have a jump across the sample. This is your delta T. And with the known thickness, this is basically this is definitely what you need is thickness of the material. You can use, you can determine your values. So this is just a picture of our TIM tester, the solution for the TIM world. This is a very sensitive and precise machine, and we used everything what we know and what we're good at in this field in our new tester. So why can't we use the tester itself and just yeah, put high temperature cartridges in and test it at high temperatures, the cell spaces? You will very soon run into a problem that you have extreme heat flow losses to the ambient in your hot side. So you might have heat flow losses on the hot side, but you might also have heat gains on the bottom side, which would basically not work for determining this kind of for this kind of materials, the thermal conductivity. And here's the solution of our guarded heat flow method. So basically we have two parts also. We have a hot side here, which is shown. It consists of a cool plate, which basically stops the heat from going to the system itself. Then we have an insulation, and then the heater itself, which consists of five individual cartridges, which are controlled individually to each temperature sensing point below. Then we have the bottom side. Here, the centerpiece is basically the heat flow meter in this area. This is the guard ring, which I will talk more in depth just now. Also, we have a heat sink on the bottom side, basically as to cool the cold side. And then we use a laser micrometer, like also with our TIM tester, to measure the thickness of the material. Now you can see the cross section of this measuring part of the system in this area. Yeah, well, if we focus on this area, you can see here now a thermal simulation, which we did to develop this kind of testing. And here, this area is the centerpiece. This is the guarded heat flow meter in this area. And just the theory tells you that if you're using a meter bar, you need straight heat flow lines. As soon as you have bent heat flow lines, you're making an error because you're measuring temperatures, and you use those those temperatures with the known properties of your meter bar to determine the heat flow meter. And the guard itself, you can see, actually has quite a bit of heat gains from the ambient. This is basically radiation from the upper side. And then the idea is basically to have a gap between the heat flow meter itself and the guard. And now you can see you have quite straight heat flow lines, and you can measure precisely your needed heat flow, which goes through the sample. So this is yeah, a closer view in this area, and just the the sample area is 100 times 100 millimeters, and the actual measuring section is 50 by 50 millimeters. So you can here see, compared to the TIM tester, we're using one thermocouple on the hot side and then two in the heat flow meter. And this is basically just all the values basically which you're measuring. It's the hot side temperature, it's the thickness, and it's the two temperatures in the heat flow meter. And now you can determine your thermal conductivity, thermal resistance of your sample. Okay, so we did a simulation study, and with it we can determine how big the remaining heat flow is. This is basically considering geometry, the temperature level, losses, and to the ambient. And here is the exact same um, field without using a guard, so basically just a cold plate. On top side, you have the thermal conductivity, and here you have a thickness. And you see in the range of higher conductive materials, you don't have much of an issue. You can use just a plate without the guard. But once you go into the low conductive thick materials like aerogels, you have an increased error just through the losses, basically the heat losses. Then this is our exact error field with the guard. So you see you still have an impact because there is some heat exchange between the guard and the heat flow sensor, but it's not as intense as here. And you have an elevated error field, which is basically the gap which you included in your sensor, which is basically increasing the error across all thermal conductivities and all thicknesses. Yeah, let's get to the test itself. You can see here in the picture, it's approximately man-sized. It's much heavier. It includes a fume hood, which is attached to your ventilation system, or it can have an internal fan to remove the fumes and the smoke. Included is a high precision chiller, which is very important for this kind of testing because the heat flows going through the sensor can be very low. So in this instance, let's say when we have 35 degrees Celsius on the top side and 15 on the cold side with a aerogel sample and 6 millimeter thickness, we're only having about 1 watt going through the sample of 100 times 100 millimeters. In our instance, this is 0.1 Celsius in the heat flow meter. Now you can imagine if you have a chiller which is plus minus 1 degrees, you won't have steady state ever. You will basically oscillate across or in sync with your chiller regulator. Then the test itself has a electrical drive unit, which you can realize pressures from 0.002 megapascal to 4 megapascal, which at this area is about 20 newtons, so 2 kilos to 40,000 newton, which is 4 tons. The drive unit itself, it's possible up to 200 millimeters per second, but we are at this point, yeah, we are put a stop at 10 millimeters per second, and you can test your materials with your individual profiles on force control and thickness control or both. And yeah, it's compared to let's say a hydraulic version. It's low maintenance. Then, yeah, as I said, the heater itself consists of 5 individual cartridges, which have individual power supplies. And the maximum power at this point, which might be increased in the future, is 2.2 kilowatts, which at the 850 Celsius, about 50% can go through the sample. The other 50% are basically losses to the ambient or directly to the upper heatsink. So the test itself was yeah, we're about 8 months, which the first one was built. So we have about 6 months now experience with our tester at our lab. So we already have sold one to North America and one to Asia. And yeah, it's built basically for us in the lab, so it's easy to clean and to maintain. And the heaters itself, which is a critical part, they are robust, like the experience shows in the last 6 months. And yeah, one thing I want to say is we have 3 individual testing points in the heat flow meter. So you don't have just one thermocouple in this area, but 3. So you can also test your materials on how homogeneous it is. You can derive data with one test in the material. So the thermal conductivity, you need to measure the thickness of the materials. And what we do is we use a laser micrometer, which is the same as in our TIM tester. Basically, you have in the lower meter bar and in the upper heater, you can maybe see it here, you have a pin sticking out. Which one laser sends out a beam which casts a shadow to the sensor, and then you can very precisely measure the thickness of the material. So with this tester, you can go up to 25 millimeters. And the accuracy depends on the temperature. So at room temperature, you are yeah, below 10 micrometers. At elevated temperatures, you have a little bit of warpage, and you're in an area of plus minus 80 micrometers. And this is for us basically at this point the main focus of the optimization is to increase the accuracy of the thickness measurement. And for the thermal resistance, the thickness is not important, so it doesn't, the precision is not important, so to speak. So then important for us is a heat shield. You can see it in this area with the a glowing hot heater on the top side. This is at 850 degrees. So the heat shield prevents thermal radiation reaching the sample. At 850 Celsius, the radiation itself is enough basically to start burning of of a of some samples. So yeah, we included a heat shield to protect it. The software is also developed by us, and yeah, it's because we use it and we are yeah also pushed by our customers. It is yeah ever expanding and yeah so with regular updates. So the tester itself has obviously also limitation. One limitation is the finite heating power. So you do have very low conducting materials, but still at this temperature gradients, there can be a lot of heat going through the samples. This is what I try to show with these graphs here. So at 850 Celsius, in the green area is basically testable. The red area is you would need more heating power to be able to test these areas. So you can see like an aerogel sample in this area. You can test it all the way. And then once it increases, you will reach a point where very thin materials might be borderline. So this is maybe in our experience for about, I don't know, maybe 2 to 5% of the samples we receive are too high conductive basically to test it. And then at lower temperature, the red area gets smaller, and at low temperature, you can basically test through the whole spec for all thermal conductivities and yeah, the all thicknesses. So another limitation is the limitation due to sensitivity of the heat flow meter. This example, as I shown before, with the even lower temperature at 25 Celsius, and you are only having 0.3 watts going through the sample. So this is basically the warmth a bee generates in that area, the heat going through a sample the size of your hand. So that's a very low temperature difference in the heat flow meter. As you see here, you're only at 0.03 Celsius. And this is not a sharp border. You can test it or not. This is basically a border which we say, okay, we're comfortable to that area. But it's a question of uncertainty, so to speak. And yeah, this is a problem at very low temperatures. So you temperature gradients, and at higher temperatures, you will be in a better area. So usually when you receive results from us, in the result graph of the thermal conductivity or the thermal resistance, there are error bars, and the error bars are usually much bigger in the low temperature than at the high temperature, which yeah, it's probably not intuitive, but that's the reason for it. And yeah, here you can see such results. So what are typical testing parameters? This is very interesting. We are still in an area where basically, I would say, most customers of us, they don't actually know really how to test the materials. And this is something which we have established with a couple of car companies here and in Asia. So it's a test which includes three different kind of tests. So we run a steady state cascade, which pressure. So we have a low temperature typically on the hot side. It can be 35 degrees on the hot side. It can be 50 or 80. And then we test the material across 6 to 8 individual pressure points, as you can see here. So here you have the thermal conductivity. Here you have the pressure all the way to 4 megapascal, and then the individual points. The same for the resistance and the sample thickness. You have graphs shown here. Then the next testing cascade is temperature. This is done typically at low pressure. So the wish is always basically no pressure, which is not impossible, which is impossible. You need some pressure to contact. This is done at around 0.002 megapascal in this area. And then we have 4 to 8 individual hot side temperatures. So you can see here now the thermal conductivity of the material. And here you see an increase of the thermal conductivity. It typically always increases, but you can see all kind of different behaviors from this materials, which is not really which we're not really used to, let's say, with our TIM tester, or this is just these effects which I talked about in the beginning. You have evaporation, you have slow evaporation, you have chemical reactions, and yeah, this kind of effects you usually don't have in other kinds of testing. And the third test is a test which is closer to the real application. So um, the the application is a fast process. So we're talking minutes. So the battery goes off. This is a maybe in 60 seconds, 180 seconds. So different kind of theories. And we have a steady state method to determine these behaviors. And the third test basically wants to include this transient behavior in our testing, and that is our so-called hot cold side test, which is a temperature shock test. So what we do is we preheat the top side, as I shown in the picture before. We have the heat shield inside, and once we're at steady state at the hot temperature, we're compressing very fast to a either gap or to a or sample thickness or a pressure on the sample, and then we plot the temperature behavior on the cold side and the thermal conductivity. This is shown here. So in red you have the hot side temperature. So here the starting point was 600 Celsius. So in the beginning we have a little bit of a impact on the compression on the heater itself, but you reach your goal very quickly. And then you have, depending on the sample, in a couple of minutes you will reach steady state. So yeah, it's a good third or safe test to make sure that the material also behaves in temperature shock the same as it does with the slow heating up of the cascades. So here we have a video. Let me see. I do have a problem with starting it. So this is now the hot cold side test, for example, at 650 Celsius. This is the heater. It's now not glowing because we are at a lower temperature. Then you have the heat shield, and here is a sample which I built for just to show you. And once we are at once we achieved our temperature, we will basically receive our heat shield and automatically go to our set parameters. Now you see the material starts burning just by the radiation. Then we go to contact and we start our tests. And typically this hot cold side tests lasts anywhere from 3 minutes to 10 minutes, depending on the customer wishes. Okay, so yeah, with our drive, so you can have customer specific profiles. So you can go, let's say, in 2 minutes to a certain pressure. Then you can have for 1 minute a sample thickness, then go back again to the pressure. And this is used to mimic basically the real behavior of the tester. So once we had our first prototype of the tester, we had a little bit of an issue of good quality materials to one have as a reference and the other to test the reproducibility. And just maybe 6 months ago, we received some samples from a customer of ours, which which is a very high quality material of a cell spacer. And here you can see the results of this kind of hot cold sand tests with 5 individual samples. And yeah, you can see it's quite reproducible with still all the things going, fire, smoke. So we are here in this case approximately of 1%. So in our experience, it depends very much on the quality of the sample, which often is because it's in, research, it's not machine made, it's made in the lab. It's not ideal for this kind of testing. Okay, yeah, then coming to the end. So, what is the outlook? What are we working now? So we are currently having the steady state method, and our idea is to include a transient characterization of this material. So basically to determine the thermal conductivity from the very first second, the real life thermal performance. And then also we want to increase the temperature control of the material. Currently, it's a little bit slow because there is a lot of mess in the heater. And yeah, we're working on it to mimic the real life runaway battery. And yeah, and all what we do is basically we're still keeping in mind that we want to upgrade our existing tester because we also have one, and yeah, it's also beneficial for us if we upgrade it. And then I just one last point. So I already mentioned that we have a lot of customers. I would not say that some of them are a little bit lost because they don't know how to test it, but sometimes it feels like that. And what we are organizing at the moment is a joint project called Cell Spacer. Joint projects we've done also quite a few in the past in different kinds of fields. And the idea is basically to have industrial partners and us. And we are doing a study. In this case, we want basically to have a overview of a lot of materials on the behavior, how to test them, and what are the guidelines for the selection of this kind of materials. And yeah, the results of this project, which is planned to go 18 months, is only shared with the partners. So if you're interested in that, you can contact me directly, and you will receive a little bit more information in this regard. Okay, I do have some issues here. Okay, yeah, that's from my side. If you have um, yeah, um, if you're interested in further information, you can contact directly C-Therm or us, and we will discuss it. So yeah, thank you very much, and yeah, I'm happy to answer your questions.
All righty. Perfect. Thank you very much, Nikki. I'm just a couple final things to close out here. Then we'll move into the Q&A, folks. Um, so just wrapping things up from our side. Of course, if you're looking to kind of explore more, this type of content was interesting, different past webinars, technical content pieces are available on our website. From C-Therm side as well, we also offer a full suite of testing services. If these types of measurements or getting into this type of thermal conductivity space is of interest, it's certainly an area that we are happy to support. Um, here. So, you had the contact there from ZFW on screen previously. Again, here, as Nikki said, if you have questions or would like to learn about the ZFW TIM tester or the new high temperature heat flow meter, certainly happy to provide additional information on those. And of course, set you up with the right folks to go over and discuss your application needs. So yeah, that brings us officially to the end here. So, for folks interested, please stay on the line and we will now be jumping into the Q&A. And if you're jumping off at this point, thank you very much for joining. And once again, thank you to Nikki here for taking us through today's content.